All right, so today we're going to start a discussion which will last probably a couple of lectures, the last two lectures, on vibrations in solids. And we will give it a more precise name, phonons, although what we mean, of course, just oscillations of the nuclei around their equilibrium position and trying to understand their dynamics. So before we enter into the details of what happens in solids, in crystals, let me just very briefly analyze a much simpler situation, which is that of a diatomic molecule. Suppose you have a diatomic molecule. You can think of it as the H2 molecule, for example, right? So you have a nucleus, two nuclei, two electrons. Well, I'm drawing here balls and sticks, but you know what I mean. I mean the Coulomb potential here and here. I mean two electrons that are somewhere around the two nuclei, forming a bonding state, and therefore lowering their energy in order to minimizing their energy quantum mechanically, and forming a state which is what we saw at the beginning of our classes, was then a bonding state, a covalent bond. Now, the discussion we made at that time was essentially based on the assumption that the nuclei were fixed to their positions, whatever they were. So we fixed somehow the distance d between the nuclei. Notice that I make a distinction between nuclei and electrons here, actually between nuclei and atoms. In our language, there is no such a thing as an atom, as an entity. Once we bring together two atoms, the concept of an atom itself is totally lost, because we are talking about two nuclei and two electrons. We cannot tell any longer whether the electrons belong to one nucleus or another one. So the concept itself of an atom is totally lost in our language. Okay? So here, when we say that there are two atoms at distance d, we don't mean atoms, we mean the nuclei, the point-like objects that we call nuclei. Okay, the molecule itself is an object which is composed of two nuclei and two electrons. So it's a three-dimensional object, and what we mean by this d is the distance between the nuclei. Okay, so when I draw balls and sticks, what I actually mean is the two nuclei plus the cloud of electrons that surrounds them. We claim that we calculated the ground state wave function for this system, that is for two nuclei at the distance d, and we found that this energy is lower than the energy of the two nuclei when they are at infinite distance from one another. So in principle, we could think of, as a function of d, reporting here the energies that this system has as a function of d. We certainly know that at long distances this energy has to go to zero, because at long distances there is no interaction between the two atoms. Now we can call them atoms because at infinite distances they become atoms again. At some distance we know that the energy is below the infinite limit, because there is a gain of energy. It is also clear that when you go to two short distances, if we bring the two nuclei too close to one another, there are going to be a number of effects. First of all, there's going to be repulsion between the two nuclei. As soon as the two nuclei come too close to one another, the electronic cloud is going to be surrounding them, but it's not going to screen the interaction between the two nuclei. So the two nuclei will start to repel. Secondly, of course, the electrons themselves, if you bring them too close, will start to repel because of Pauli principle. So there are a number of reasons that cause at short distances a repulsion between the nuclei. Right? So if you go to two short distances, if you bring the two nuclei too close to one another, now let me actually, the electronic cloud will be like this. If you bring the two nuclei too close to one another, then of course you get some repulsion. For a number of reasons, not just because of Coulomb repulsion, but because of several physical mechanisms. Okay? So if you, just continue analytically this curve, you clearly see that this curve must have a minimum somewhere. tends to infinity at long distances and tends to, and there is a barrier at short distances. The nuclei won't be able to get closer to than a certain distance. So this curve here, this is, say, the energy as a function of D. And it's rather universal, right? We've already discussed this at the beginning of our classes. I mean, it's a rather universal curve in the sense that almost any pair of atoms, if you take any pair of atoms in the periodic table, there's going to be some finite, a negative binding energy, so a positive, a net binding energy, again, in coming together. There will be an equilibrium distance, if you wish, that two pairs of atoms like to take when they get together, and then there will be a repulsion at short distances. So this kind of curve is rather universal. It may take different shapes. It may be deeper. It may be the equilibrium distance may be at longer distances, and so on and so forth. But the shape, the qualitative shape of this curve for any pair of atoms in the periodic table is going to be similar to something like that. So it's a rather universal concept, I should say. Morning. Now, a molecule like this, if you take two atoms like this, will certainly, this curve, what it's telling us is that there is an equilibrium state for the system, and the equilibrium state of the system is when the distance is this and the binding energy is this, is maximized. That's the minimum state. But of course, as you certainly know, the molecules are never in their precise, ideal minimum, right? The temperature, for example, as well as other perturbations, cause the molecule to vibrate or to, well, let me say, before I introduce vibrations, let me say the position of the nuclei may be different with respect to the equilibrium one. So it may be somewhere here, for example, shorter or longer, depending, on the conditions. And clearly, what we have here is going to be a vibration around the minimum. And of course, if you can approximate this to a parabolic potential, to a square potential, the vibration is going to be a harmonic vibration. The question, of course, is if you're going to be close to the minimum. So the question is, at standard conditions, say at room temperature, for example, take a molecule in, say, the O2 molecule, N2 actually, right? Air is abundant of N2. 70% of the air we breathe is made of N2, right? It's N2, and then there is a little bit of O2, and then there are other gases in the air, right? I guess you're all familiar with this, right? So air is made of diatomic molecules, which are very similar to this one, and which vibrate according to this curve. So the question is, for example, at room temperature here, in this class, you take an N2 molecule, what does it do? Where does it oscillate close to the minimum? Is it really at equilibrium? Is it oscillating back and forth this potential? What is it doing? Well, of course, it all depends on the scale of energy here of this plot, because we know, that at a given temperature T, the height of the oscillation, the maximum potential energy that you can gain in oscillating at a given temperature is of the order of kBT. I hope you're familiar with this, right? For an harmonic oscillation oscillator at a given temperature T, the average value of the potential energy is 1/2 of kBT. Are you familiar with this or not? Yes? No? Almost. Almost. Equipartition of energy. You've done it, right? So an harmonic oscillator if this is the energy of an harmonic oscillator, if the harmonic oscillator is oscillating at a given temperature T, well, if you have a collection of oscillators at a given temperature T, it doesn't make sense to have a single oscillator at a given temperature. If you have a collection of oscillators at a given temperature T, the average value of the kinetic energy and the average value of the potential energy, these two objects, they are both 1/2 kBT. Of course, for each oscillator, for each degree of freedom. So in 3 dimensions, it would be 3 halves kBt, and if you have n particles, it would be 3n over 2 kBt. So same here. I'm saying kBt, but I should actually say 1/2 kBt. Actually, 1/2 kBt is the average value of the potential energy. If you look at the maximum value of the potential energy, the maximum the maximum potential energy is when the kinetic energy is 0. So this is going to be kBt. Okay, so we are in that range of energies anyway. And if you are at room temperature, let me forget about the 2. I mean, this is just orders of magnitude. At room temperature, kBt is 25 millielectron volts. Okay? If there is one thing that I want you to learn during this course, is this one. So the question clearly is, we are close to the minimum here if 25 millielectron volts is much smaller than the depth of this curve, right? If the depth of this curve is much larger than this, then clearly here we are close to the minimum, and we can approximate it to an harmonic motion. But this energy here is the binding energy, is the energy it takes to form a molecule, right? And we know that for standard covalent systems like N2, O2, H2, this covalent energy is of the order of electron volts, 2, 1, 2, 3, 4 electron volts. So this is of the order of electron volts, at least for a covalent bond, for a strong bond. So clearly here we are at least 2 orders of of the order of 2 orders of magnitude below that binding energy. So at room temperature, we can say that at least standard systems like covalent objects, covalently bonded objects at room temperature, we can safely say that these are oscillating within the harmonic limit. At least if we talk about molecules. So the molecules that we breathe, they are harmonic oscillators, to say, with small corrections to the harmonicities. But this is, of course, not, there are exceptions to this. And exceptions can happen for 2 possible reasons. Either the temperature is not room temperature goes up, 1,000 Kelvin, 2,000, 10,000 Kelvin. Think of molecules in the sun, for example, or in planets, or in hot bodies. Temperature in the sun, for example, temperature at the surface of the sun. How much?
10 raised to 5.
Sorry?
10 raised to 5.
10?
Raised to 5.
Yeah, that's actually the temperature inside the sun. At the surface of the sun is 10 to the 4th Kelvin. Okay? So let's say 10 to the 4th, 10 to the 5th. Actually, if you go to the center of the sun, I mean, you get to 10 to the 7th, 10 to the 6th, 10 to the 7th. So it starts from 10 to the 4th, and you go up to 10 to the 7th, and in the sun, for example. Even inside the Earth, I mean, the center of the Earth is 5,000 Kelvin, roughly. Okay, so we're talking about 10. Planetary temperatures are 10 to the 3rd, 10 to the 4th, up to 10 to the 6th. So we are talking about 1, 2, 3, 4 orders of magnitude larger than room temperature. Well, actually, you probably know the conversion, right? That I don't know it exactly, but 1 electron volt is about 11,000 Kelvin. Does anybody know a more precise number? It's probably in every textbook, Ashcroft and Mermin. But anyway, rough conversion is that 1 electron volt is 1,000 Kelvin, right? This is 300 Kelvin. So you see, I mean, there's, roughly speaking, it's like this. It's 12,000 Kelvin. So if we are at 10 to the 4th Kelvin, that kBt corresponds to about 1 electron volt. So if you go to 10,000 Kelvin, you're getting to temperatures which have become comparable to the bonds. So you can have molecules dissociating due to the thermal motion. So clearly, in those ranges, the molecules will be oscillating back and forth, a very wide range of this potential. So clearly this is not going to be harmonic. In fact, emission lines vibrational emission lines due to molecules in hot bodies, they have a number of effects that are characteristic of anharmonicities in this system. So there are two possibilities. Either temperature is very high, think of a hot body like the sun, like surface of the sun, for example, surface of stars, or plasmas in labs. The other possibility is, of course, that the binding energy is small, not electron volts, but it's small. We discussed several possibilities for the bond strength, and remember we discussed, for example, the weakest one is the van der Waals bond, right, between neutral objects. Take two methane molecules, for example, two helium molecules, or rare gases, argons, and things like that. Their binding energies are of the order of kBt, milli-electron volts. In fact, these systems, when you really realize that when the binding energy is comparable to temperature, it's not even obvious that the two objects like to stay together. They might prefer kinetic energy might prevail, and the system might behave like a gas. Notice that I'm talking about the gas in terms of this coordinate. So if two objects, like two helium atoms, for example, their binding energy is of the order of millivolts, of milli-electron volts, at room temperature, helium doesn't want to form a solid. It doesn't want to, the two atoms don't want to stick to another because the kinetic energy prevails, the temperature prevails, and they form a fluid or a gas, actually, at ambient conditions at room temperature. Okay, so this is very important as a concept, and the important quantities to look at is the binding energy as compared to the temperature, of course. If the temperature is low with respect to the binding energy, as it is the case for a number of systems, then the system will be just vibrating. There are actually systems, very simple ones, like even air, right? Let me be a bit clearer about it. In a gas, there are actually several degrees of freedom, not just the internal one. There is also a translational one. So you may also wonder what is the energy of interaction between one molecule and another one. This is completely different scale of energy because the interaction between two atoms has a very deep well, it's very strong, electron volts, but the interaction between molecules is very weak. Two nitrogen molecules, two oxygen molecules have an interaction, a binding strength of a fraction, of the order of probably of this order, precisely of this order, actually a bit less, right? So we're talking now about the translational degrees of freedom of two molecules. So we have a situation in a gas in which the internal degree of freedom is harmonic, but the translational one is completely, free particle one is completely dominated by kinetic energy because the binding strength is so small that kinetic energy dominates and the system behaves like a gas. So I guess this is a good example that shows you that even within a given system, there may be two different scales of binding, intermolecular binding and intramolecular binding, and the two bindings have completely different energy scales, and one is frozen and harmonic, and the other one is completely free and behaves like a free gas, which is a translational one. Okay. Yes.
Can we infer from this picture a high temperature? Because this picture is for low temperature, like room temperature. Can we use the same picture?
Sure. The question is if you can use the same picture at high temperature. This energies versus distance is independent of temperature. Then on top of this, you have to put a particle that behaves at a given temperature, right? So if the temperature is low, the particle will oscillate close to the minimum. If the temperature is high, it will oscillate, it will have broader oscillations. If the temperature is very high, then there is even no binding. The two particles will behave like a gas, and their attraction becomes irrelevant, like in a standard gas. The interaction between molecules exists. The two nitrogen molecules, if you look at their interaction, they do have a small binding energy. but the temperature is so large that they never reach that state, that bound state, because the kinetic energy prevails. They will see it only occasionally, but then they will approach this state with such a velocity, right? They will probably be at this value of the temperature will be very large, right, on this scale, and therefore will probably be reflected. They will see occasionally this little well when they approach another in a collision with another molecule, but this is will really last for femtoseconds. Most of their time will be spent in regions where the distance is very large, like in a gas. Okay, so these are very general considerations about, and there are considerations I should mention, I should be precise, limited to a single degree of freedom. Well, we've extended it to consider 2 degrees of freedom, 2 different degrees of freedom, but there's, this curve is limited to a single degree of freedom at least. Okay, let me now move on to solids. Let me first approach the problem from a phenomenological perspective, and then we'll do some calculations. So if you're in a solid, we have an ordered system of nuclei, and there will be electrons everywhere, right? Block states. At finite temperature, of course, we cannot expect the nuclei to be sticking to their equilibrium position. Precisely like a molecule is vibrating, we should expect also our nuclei, which carry a mass, the nuclear mass, to vibrate in this system, right? So in a molecular system, the obvious degree of freedom is the stretching. Here, of course, every single nucleus will be moving in a 3-dimensional potential. So this particle, for example, will be oscillating back and forth, and I'm now drawing here the trajectory, right, of a nucleus at finite temperature. So we'll never be exactly in the equilibrium position, but we'll oscillate around this equilibrium position with some frequency, hopefully, and we'll get back to that in a moment, and with some typical oscillation width, which is characteristic of the restoring potential that this nucleus has around the equilibrium position. Of course, all the other nuclei will do the same. They will, They will vibrate. They will oscillate around their equilibrium position. In fact, if I'm allowed to keep the nuclei fixed, all the other ones, and just focus on this one, well, you may argue that if this is a minimum of the energy, I can certainly say that there will be, if I, say, look around myself, okay, if I consider, say, this as R, and I look around myself, if this is a minimum of the energy, if this is an equilibrium point, I can certainly say that there will be a parabolic confinement around this point. If I can keep all the other atoms fixed to the equilibrium positions. So suppose I do this experiment. Of course, I cannot do it in practice, but I do it in a sort of ideal experiment in which I fix all the other atoms and I let this particle do whatever it wants. Then, of course, I can, if this is an equilibrium point, if I displace the particle from equilibrium, I can expect that there will be a potential like that around myself. Of course, this potential will depend on the direction. Depending on where I move, I will feel a slightly different potential. Clearly, if I move along this direction, maybe the potential is stiffer, right? Because I'm moving directly against another atom, another nucleus. If I move along this direction, perhaps it is a little bit softer, because this atom is further away. So depending on where I move around myself, there will be some restoring potential with different stiffnesses, depending on the direction. But certainly what I can say is that if it is a minimum, there will be some sort of quadratic expansion around the minimum which keeps me there, and then the particle will, of course, be oscillating around this parabolic potential with different say, curvature in different directions because of the anisotropy of the environment that I see around myself. At some point, this potential will stop being parabolic and will start behaving in a non-parabolic way. After all, the reason why this is kept here is because it is interacting with the other atoms, and with each other atom, this atom is experiencing an attractive force, or a potential of attraction that is very similar to the one that we had at the blackboard previously. So the potential will be, of course, periodic at the beginning, but then it can take any arbitrary shape. In fact, we know that if we increase temperature, now let me put temperature, for example, here. If temperature is here, the particle will be oscillating almost harmonically. If the temperature is lower, it will be more harmonic. At some point, we will reach a point in which this harmonic motion is no longer a good solution, and the particle will start to move around throughout the crystal. It's a bit like the situation we've examined before. We have a confinement, but if the temperature is large enough, at some point, there's no reason why the two particles should be together. At some point, it behaves like a gas or like a fluid. The particle will start, the kinetic energy will start dominating if we go sufficiently high in temperature, and the system will become essentially free to diffuse in space. But we're very familiar with this situation, right? If we increase temperature, the vibrations will increase, the average distance from equilibrium will be larger and larger, and at some point, a crystal melts, right? Any crystal at some temperature will melt, and melting means that at some point, the particle will start to diffuse freely in our crystal. Okay? In fact, there is even a rule of thumb, which is verified to an impressive precision, even though it's not a theoretical rule. And that rule states that as soon as the averaged amplitude of the vibration around the nucleus exceeds something between 15 to 20% of the distances between atoms, then the particle will become to diffuse freely. The system will melt. There's no theoretical support for this, but it is actually verified with an impressive precision throughout the materials that we know in nature. So, well, we can take it as a phenomenological rule. So the rule states that as soon as the amplitude, this amplitude d of fluctuations of a particle around the nucleus exceeds something of the order of 15 to 20%, well, 0.15, 0.2% of the interatomic distance A, as soon as this happens, as soon as the temperature is such that this condition is violated, that is, the distance becomes larger than 15-20% of the interatomic distance, 99% of the materials will melt. Whatever that, it's a very, I think it's nice to mention it because it gives you an idea of when you should expect that thermal vibrations essentially kill the crystal and lead the system into a fluid, into a melt. And of course, the stiffer the potential. Now think of it. Now think that this is verified. Whatever that means, it's an empirical rule. And now think of varying the stiffness of the potential, the curvature. Now, the more the curvature is stiff, the more, in order to achieve this condition, you have to go high in temperature, right? Because if this condition tells you that you have to reach this value for D, right? The stiffer is the potential, the higher will have to be your temperature in order to reach that condition. So if this rule is valid, we can conclude that the stiffer is the potential, the higher will be the melting point. The higher will be the temperature at which the system will melt. And this is, in fact, well, it's probably obvious to state. If you have a system where the bonding is strong, where this attraction of the atoms to their equilibrium position is very strong, that means atoms don't like to move from their equilibrium positions because they're kept tight together by strong bonds, then you should expect the melting temperature to be large. All right, so this is just phenomenology for the time being. Let me try to go a little bit more precise with mathematics. What I need to consider, and I didn't consider here, is the fact that when this nucleus is moving, all the other nuclei are also moving. So my initial assumption that there was a nice potential, a quadratic potential like this, was based on the assumption that I was keeping all the other nuclei fixed. But the other nuclei are not fixed. They actually move themselves. So when this nucleus is moving, this nucleus is also moving. So how can I describe the dynamics of a system like this, in particular of each individual nucleus, if all of them are moving, not just one of them? I need to somehow come up with a mathematical framework that allows me to describe the collective dynamics of all these systems, not just the dynamics of one, or the center of, or the interatomic distances like we did in the case of the molecule. I need to be able to do this in a collective way, not just by looking at the dynamics of a single one. It is indeed a motion, the motion of this nucleus, it is indeed correlated with the motion of all the other nuclei, because you can easily imagine that if this particle happens to be here by chance at some point, the potential that this particle feels is different with respect to when the particle is here, right? Because when this particle is here, it's very far, and therefore perhaps the curvature will be softer. If the particle is here, the other one I mean, if the other particle is closer, the potential of interaction will be much stiffer. Okay, so the dynamics of this object will be tightly correlated to the dynamics of the other one, of course. And similarly with all the other atoms. So this leads us to consider a very simple model, which you might have already seen, the linear chain of oscillators, but I would like to do it anyway because it's a very simple and instructive exercise. So the model we're going to use to describe the dynamics of this complex correlated system is we're going to assume now that we are in one dimensions, that particles that have a number of particles with the same mass okay, at the distance a from one another. And I'm going to assume that the interaction of this particle here with this particle here, as well as the interaction of this with this, is a harmonic interaction. Okay, so I'm assuming essentially that the interaction of each atom with another atom can be approximated with an harmonic spring. Now, this is, by the way, equivalent to saying that I'm considering the energy of this system, the total energy of this system, as a sum ij of let me call E dij. So suppose I can describe the interaction between atom I and atom j using this universal function that we described before. Okay? So suppose that each atom is interacting with another one with the same function that we derived before, this E of d that we had at the blackboard at the beginning. if I put together an infinite number of, or a collection of atoms, I can, within some approximation, state that the total energy of my system is the sum of all the interaction energies between all possible pairs of atoms in my system. Actually, I need to put the 1/2 here if I'm summing over all i's and j's, or I do I, well, it's the same, or I do I different from I, well, I need to make sure I don't double count the energies, right? If I include 1 and 2, I don't have to include 2 and 1. So I have to put a 1/2 and also put here this in order to, this means that I is different from j, typically. It's a typical notation to say that I is different from j, a prime in the sum. So I'm trying to justify my model here. I'm trying to justify my model by stating that if I take a collection of atoms, I can expect that the total energy of my system is going to be given by the sum of the pair energies of interaction between any possible pair of atoms in my system. Now, I would like you also to, however, realize that this is in itself an approximation. If I have two particles that I know interact exactly with this function, I have two particles, and I know I calculated to infinite precision, or I measured with infinite precision, that the interaction between those two particles is given by this function. Let me now introduce a third particle here. If this was not there, I could calculate the interaction between this and this to infinite precision. If this was not there, I could calculate the interaction between this and this with infinite precision. Whether the total energy of the combined system is the sum of the three is not obvious, because the interaction between this and this might be affected by the presence of a third atom, right? If you think of it in terms of quantum mechanics, it's quite clear. Here, the interaction between this and this, there is a formation of a covalent bond, some charge distribution. But then if you consider there is a third atom, this bond here, this charge density, might be affected by the presence of the third atom. And similarly for all the other pairs, of course. So I want you to, be sure you understand that this is just an approximation. It's not an exact theory. However, let me assume that I can approximate this interaction by a sum of pair interactions, interaction between pairs, which is, again, not necessarily the truth. It is a good starting point, at least, to describe the interaction between a collection of particles. Here I have interaction of this particle with this one, this with this with this, all possible pairs. But clearly, if I sit here, for example, let me put a label here, I, and this is I plus 1. I'm using the same notation I used for the hydrogen atom chain. The interaction between this and this is given by this energy at the distance a. The interaction between this and this is the same energy at distance 2a's. So clearly, I can at some point truncate my sum, because the potential, this energy here, is going to go to 0 at some distances. So when I consider interaction between this particle and all the other possible particles in my system, clearly, at some point, I can forget about, including those interactions in my sum. I can stop. Well, what we're doing here is actually to stop after the considering only the first nearest neighbor. So let me assume now that in addition to this approximation, I'm going to limit the sum only to nearest neighbors. So this interacts only with this and this. I minus 1 interacts only with I and with I minus 2. It's an approximation. It's the spirit of the approximation we introduced for the tight binding model, you may remember. Physical interactions have a finite length, range of a finite extension. So let's truncate, if we want to build the simplest possible model, let's truncate our interactions to first nearest neighbor. So I can actually further approximate this to interaction between first nearest neighbors, if I wish. if I accept all these approximations, what I'm left with is oh, sorry. If in addition to this, I consider that my temperature is low enough that I'm close to the bottom of this E versus D curve, that is in the harmonic part of this curve, then clearly you see that this is exactly the model that I described at the beginning, where each particle is interacting with a spring with an harmonic potential with each one of its nearest neighbors. Okay, so I just wanted to somehow derive, of course, very phenomenologically, why we can, at the end of the day, consider a model which is that simple. I now summarize all the various important approximations that we're making when we derive this model. Okay, so we have a model in which each particle is interacting with the other one with a spring. So there will be an energy contribution which in 1/2 k times the actual distance between the two particles, right? Which, mind you, may not be necessarily A. Sorry, oops, D minus A, of course, squared. Which says that at equilibrium, if the distance is exactly A, I'm at a minimum. If the distance is larger or smaller than A, there will be a restoring force trying to bring the system back to A. And this will be the case for all, so let me put my springs here. Springs that will try to bring back the system to the equilibrium distance, essentially. And we know what this means, right? We know how we can get to this point. And this K, of course, is nothing but the curvature or our energy versus D. Just the curvature of the lowest part of the potential. So let me sit now on atom I and try to move atom I away by an amount U from equilibrium. Okay, so let me call U of I the displacement of atom I from equilibrium. All right, U of I can be positive or negative, depending on whether I move the particle to the left, to the right, or to the left. So if I apply classical mechanics, the force that particle I will feel, which will of course be acting on the coordinate U, the coordinate of the particle, will be given by two terms. There will be a force due to atom I plus 1, which will try to push the atom back, and there will be a force due to atom I minus 1, which will try to push the particle again back to equilibrium, right? So there will be a term, let me first put the term to the right. There will be a term which is proportional to K, Ui minus Ui plus 1. Notice this. In fact, what counts is not just the distance between, it's not just Ui versus the ideal position, but it depends where particle I plus 1 is. If particle I plus 1 is moving in the opposite direction, the actual length of the spring is going to be reduced, right? So what really counts is the distance between I and I plus 1, which is the difference between Ui and Ui plus 1. Right? So the force felt by I due to atom I plus 1 is going to be given by this term. It's essentially the length, how much I reduce the length of the spring. Is it okay? You look. Then there's going to be another force due to atom I minus 1. Yes. And this will be also given by minus K Ui minus Ui minus 1. So again, the distance between I and I minus 1 which is ui minus 1 is here, and then minus k, which is the restoring force. If you're not convinced about the signs, think of it, let me do it with the correct. Suppose that ui minus 1 is 0, okay, so that this particle is at the ideal position. If I move ui to the right, positive, the force must be negative, right? It must bring the particle back. If I move it on the negative side, the force must be positive. So the sign in front here must be negative. And also the sign of ui and ui minus 1 must be opposite, because clearly if the two particles move in opposite directions, you are increasing the effect, right? You are shrinking the bond even further. So this is a simple way to make sure that we have the signs correct in this expression. Okay, so here I have k ui plus 1 minus 2k ui plus k ui plus 1. So the dynamics of atom I is affected by where atom I is, obviously, but also where nearest neighbors are. And we are assuming in our model we are forgetting about second nearest neighbors and onward. Okay? But the important thing is that the dynamics of atom I is now correlated to the dynamics of atoms I minus 1 and atoms I plus 1. What this means is that this is a system of an infinite number of oscillators. This is a linear system of oscillators, a moment, which are all coupled to one another, because I is coupled to I plus 1. I plus 1, of course, will be coupled to I plus 2, and so on and so forth. So it's a system of infinitely many oscillators, all of them coupled to one another. Yes? Yes, so U is the displacement of the particle from equilibrium. Yes.
Then, okay, so we have to say we want okay, so we have to say D, okay, if it was D or A minus ui minus ui plus 1, right?
So in this particular, okay, so
Change in names
yeah,
between the equilibrium.
so the potential is 1/2 d minus a squared, okay? In one dimension, this object is ui, well, if I'm considering this bond, for example, is ui minus 1, right? Because the change of distance between these two particles is going to be given by, okay, let me... Suppose I move, for example, this ui in this direction, and this one, let me put different, I minus 1. What is the total length now of this? Well, not, minus a. I have to calculate d minus, of course, the equilibrium distance, which is a. Now, this is ui positive minus ui minus 1. Okay? So ui minus 1 is the sign is irrelevant because I'm taking the square. The important thing is the relative sign between ui and I minus 1. They must be opposite, because if they go in opposite direction, they sum up. Their contribution sums up. Okay. So from a mathematical point of view, we are, yes? No, it's plus. Sorry, you're right. Thank you. Good. So from a mathematical point of view, we're actually stuck with a very complicated problem, because it's it's a system of infinitely many coupled oscillators, all coupled to one another. There's no obvious way to decouple these oscillators. I cannot construct a subsystem of oscillators which is entirely living on their own, another system of oscillators, decouple mechanically. These are all coupled to one another. And it's an infinite set of them. So the way we proceed is by making an assumption, the first assumption, actually the only one, presumably. The assumption is that ui as a function of t is ui bar, a constant, times e to the omega t, e to the I omega t, with omega to be determined and ui bar to be determined. So this is an assumption. And we're not going to justify it. Just take it as it is, an assumption. We're going to assume that the time dependence of this motion is harmonic, with an intensity and a frequency omega to be determined. Notice here that what I mean by this is actually the real part of this object. So I'm assuming that u bar can be a complex object. In principle, this is an imaginary number. This is a complex number, right? So what is the meaning of a complex displacement? Whenever I write something like that, I always mean the real part of it. Since this is linear equations, I can always assume that there is a real part of everything somewhere to the left. So whatever I write means there is a real at the beginning. Since I'm not taking products of complex numbers, I can do that. All right, so what I mean by this is an oscillator at the frequency omega to be determined, strength u bar to be determined, and phase to be determined because this u is a complex number, so it has also a phase. If I accept this assumption, this equation becomes minus omega squared m ui bar ei omega t equals to k ui plus 1 bar ei omega t minus 2k ui bar ei omega t plus k u bar I plus 1 ei omega t. Minus 1, sorry. Oh, questo è mistake. Sorry, I should have mentioned that this assumption is a rather strong one because I'm assuming that all particles move with the same frequency, with frequency to be determined. This omega does not depend on I. The only dependence on I here is in the prefactor. So it's a rather strong assumption if you think about it. I'm assuming that all particles move with the same frequency. Will I be able to find a solution? I don't know. We'll see. If we find it, that was a good assumption. Again, nobody tells me that there may be other solutions which differ with respect to this functional form that solve the problem. So that's the meaning of when I say an assumption. An assumption, if you verify that it is a solution, it is, of course, a good solution. The question, of course, is whether there are other solutions that don't take this form, this functional form. And this is something we are not going to prove. But you can trust me, there are no other solutions other than functions of this form in the problem. We are not going to prove it. But I want you to still notice that this is a rather strong assumption because I'm assuming that each particle is moving with the same frequency. Frequency to be determined. And amplitude, which is different for every particle, to be determined. Okay, so this is now our equation. We have transformed an equation between a function of time. Okay, here this was an equation between functions. An infinite number of time-dependent functions in time. Linear equation, but an infinite equation between functions. With this transformation, I've transformed this equation into an infinite set of equations between numbers. Linear equations between numbers. U bar. and omega to be determined. Omega appears only here now because e to the I omega t has disappeared everywhere. Omega appears only here, but omega is to be determined. So here the unknowns are u bar I and all the u bars and omega squared. So I have an infinite set of numbers to determine and an infinite set of equations because all the equations with all possible i's. I mean, right, this I can be any number, so it's an infinite set of equations. Okay. Allow me to write it in a different form, this equation here. Allow me to write it in this form here. Well, first of all, allow me to change the signs everywhere. So I'm not going to do it, actually I'm going to do it with the color chokes. I'm going to change the sign here, plus, I put a minus here, plus here, and a minus here. Okay, I've changed the signs everywhere, just for convenience. And then allow me to write it in this form. I will first write it, and then we will recognize that what we've done is correct. Okay. So I've now written a big matrix equation. And I hope you recognize that if I multiply this row here with this column, okay, so that's row I multiply with this column, I get minus k u minus 1, 2k I minus k I plus 1, 0 elsewhere. And row I is equal to omega square m u I bar. That's exactly this equation here. So you have a big matrix, an infinitely large matrix, in which only the diagonal term and the first of diagonal terms are non-zero. They take these particular values, 2k and minus k. And if I write my infinitely many linear equations in this matrix form, well, it's an exact, there's nothing, I didn't do any approximation. It's exactly what I'm writing here, I'm writing it there. I'm simply writing it in a different form. I'm writing it in matrix form. And you can certainly recognize that rho I is our equation. Rho I of that equation is this equation here. And of course, any other row is also the correct one, right? Because this one will be the row centered at I plus 1, which interacts with I and I plus 2, and where here I have omega square m I plus 1, and so on and so forth, right? So it's just changing the index here to I plus 1, I plus 2, I plus 3, and so on and so forth. So in other words, I've transformed this linear system of equations in matrix form into something that can be sort of mathematically seen in matrix form. I didn't introduce any change. I mean, it's the same thing, just expressed in a different way. I'm writing in this way because now it becomes clear what our problem is. Remember, our unknowns are the u bars, all of them, infinite many, and omega squared. But this is exactly, I mean, mathematically is equivalent to an eigenvalue problem. I have a matrix which is given. I have an unknown vector to determine, and this unknown vector happens to be the eigenvector of this matrix, right? Constant times the vector itself. And this is the eigenvalue, which I also need to determine. Okay, so from a mathematical point of view, I've transformed the problem which looked a bit difficult to digest into something that is, at least mathematically speaking, clearer. The whole problem will boil down to try and diagonalize, find the eigenvectors and eigenstates and eigenenergies of this big matrix, infinitely large matrix. A very peculiar one, because there are terms in the diagonal and terms only off diagonal. And in addition, it is translational invariant. If I translate by one step, of course, in both directions, the matrix goes back into itself. Obviously, right? Because I have translational invariance. Now, I'm sure you have seen this mathematical problem again. If you go back to your notes. You remember when we did the linear chain of hydrogen atoms? There was exactly the same problem. This was the, we call them A's, right? The coefficients of the tight binding expansion. This was our energy. These numbers were different. Here we have the delta E naught, and here we have the T, the Hopin term. But apart from that, from a mathematical point of view, exactly the same problem. There is actually a peculiar thing here. Here, this term is 1/2 minus 1/2 this one. In the tight binding case, we didn't have any constraint on delta E naught and T. They could take any value. Here they have to take, in fact, there is a property that states that the sum of all these terms, the sum of all the terms along this row must be equal to 0. We will not prove it, but it can be proven actually it's a very simple proof. That the sum of all these terms must be equal to 0. So there is a sum rule on this matrix that we didn't have in the case of the tight binding method. Also, I want to make sure you don't say the analogy, I want to make sure you understand that the analogy is purely mathematical. There is no analogy from a physical point of view, because here we are dealing with a system of coupled classical oscillators. So we're in the realm of classical mechanics, Newton's equations. In the tight binding model, we were dealing with the diagonalization of a quantum problem. So from a physical point of view, we are dealing with a completely different problem. One is quantum mechanics, this is classical mechanics. Okay? The only thing they have in common is the mathematics. We have the same structure of the matrix, and we're looking for a mathematical solution which is of the same, we're looking for a solution of the same mathematical problem. Of course, there is an underlying similarity between the two systems, and this is a translational invariance of the problem. And this is what makes the two problems mathematically identical. If you wish, it is something that when we looked at the electronic states, takes the name of Bloch's theorem, in some sense. It's the consequence of translational invariance on the properties of the solution. Here it might take the name Bloch's theorem, whatever. I don't like giving names to things. I like realizing that this is mathematically the same problem, and therefore, if it is the same mathematical problem, mathematically it must have the same solution. Right? If it is the same mathematical problem, mathematically it must have the same solution. And you might remember how we solved the other problem. Do you? So for U, I bar, yes?
Okay, here, this is valid only for a crystal which is made of the same atom, right?
The same?
The same atom or...
Yeah, of course. Next time we're going to study a system where the atoms are different.
Because we have the same K.
The same K, the same masses, and same everything. It's a monatomic chain of atoms now. It's the simplest possible problem. It's the equivalent of the hydrogen chain in the beginning. Of course, that was the simplest possible example of an electronic system, extended system. Here we're studying the simplest possible example of a vibration phonon model. Okay, so go back to your notes several lectures ago. Do you remember how we solved this? We have to find an expression as a function of I, right? We have to specify what is u bar for different i's. You remember it? How we solved it? Yes, we gave an answer, right? We tried the solution of a given type. You remember it? Okay, so we have u double bar, a constant, e to the I, q, I. Right? We said, yes, let's try this and see if it works. Well, it worked in the other case, so it's going to work also now, of course. So let's try it. So let's plug this into this or into row I of our problem. Right? So we have omega squared m u bar double bar e to the I q I equals to minus k u double bar e to the I q I plus 1 plus 2k u double bar u to the I q I minus k u double bar e to the I q I minus 1. Right? So let me remove some phases that I can remove everywhere. So I'm going to remove e to the I q I everywhere. We did exactly the same for the tight binding problem, so you can look back at your notes. Omega squared m u double bar equals to minus k u double bar e to the I, sorry, not 1, sorry, mistake. It's the I that disappears here, not the 1, of course. Right? It's e to the I q I that disappears. Q plus 2k u double bar minus k u double bar e to the minus iq. Bit. Clearly, I'm looking for solutions in which u double bar is not 0. Right? If it's 0, that's not a, I mean, it is a solution, right? If u double bar is 0, all the ui's will be 0, all the functions ui of t will be 0, nothing will move. This is a solution, right? But it's a trivial solution. So I'm now going to assume that u double bar is not 0. If it's not 0, I can remove it. And what I get is, actually, let me group the things here. So I get omega squared equals to k over m 2 minus e to the iq plus e to the I minus iq is twice the cosine of q. Or, if you're good at 1 minus cosine of q is twice the cosine square of q over 2, right? Sine square, sorry, sine square, yes. Thank you. Sine square. So 4 sine square of q over 2. Or omega equals to 2 square root over k over m sine q over 2. So I'm going to repeat the same story once again, right? We've done it already several times. We've made an ansatz. We assume that the solution could be written in this way, for a generic q to be determined. We find that the resolution is possible as long as omega is equal to this function of q. So given q, as long as omega is given by this function of q, this solves the problem, solves our problem. That's exactly what the same kind of considerations we made in the case of the tight binding problem. Let me draw this function now. Okay, so it's a sine. It goes back to 0 when q over 2 is pi. So here we are at 2 pi, right? Because when q over 2 is pi, it becomes 0 again. And then it repeats periodically, right? 4 pi allow me to change the usual change of variables. Allow me to call k q over a. We did exactly the same in the tight binding problem. We wanted to do some physical length. All right, so here I'm now using k, and I simply divide this by a. I'm just changing the variable, right? Calling k, I call it q. Of course, then I have to remember that omega is, 4k over m square root, sine of k a over 2. I'm just changing the variable, introducing this variable k. All right? So, let me ask again the same question to myself. I have infinitely many solutions for all possible values of k. They all solve my problem as long as I choose omega to be this function. So if I'm here, I choose this k. As long as I choose this omega, I'm done. I solve the problem, right? Because as long as omega is equal to this, I solved my problem. So this k is fine, works, as long as omega is this. This k works as long as omega is this. This k works as long as omega is this. But again, we find a periodic function. So the obvious question is this solution the same as this one or not? This solution here, is it the same or not? Well, we have to check, right? This is the solution. If q goes into q plus 2 pi, this function is exactly the same. 2 pi times n, exactly the same. So not only the frequency is the same, but the solution itself is the same. So if I translate my problem by 2 pi or 2 pi over a in my k variable, I'm not going to add any additional solutions. I'm going to find again and again and again and again the same solutions. Every time I move by 2 pi over a, I'm going to find again the same solutions, same frequency, same solution, same everything. All right? Do I need to consider all k's? No, I can limit myself to a segment of length 2 pi over a. Which segment do I choose? The Brillouin zone. So I limit myself to this region, and I forget about the rest. Okay? Yes, be there in a second. Let me highlight now the solutions. And this is the Brillouin zone. Yes?
There are range and variables. K and K are not the same, right?
K and what?
Okay.
Oh, sorry. You're right. I always say mistake. Every time I promise that I'm going to use a different letter for this. You're right, yes. Yeah. Let me use a capital K, all right? Correct. So everywhere here, so one K, you're correct. There is a K which is the restoring constant, and there is a K which is this new variable that we introduced here. They're not the same thing, of course. They're a completely different thing. So I need to use the proper notation. I apologize for this. Yeah. Let's use the capital letters for the restoring constant and the small k for our variable. You're right. Okay? So I went a bit quick now, but that's a discussion we already made several times, so I don't want to repeat it again. The relevant part of the solutions is between minus pi over a and pi over a. All the rest is redundant. I may wish to include it, but I don't need to do it because solutions are exactly the same if I go outside the Brillouin zone. I don't need to go outside if I wish, of course. Okay, I think this is a good time to stop because next time we're going to discuss some properties of this, as well as we're going to consider another example, which is a straightforward extension of this one, in which we are dealing with a system with two particles in the unit cell, and you'll see that there are some interesting consequences on the omega versus k. All these solutions take the name of phonons. Okay, so these objects here, these solutions, the u of I as a function of q and t take the name of phonons. So this is the phonon structure, band structure. You can call it band structure because it's not. Of course, from a physical point of view, once again, we're talking about a completely different phenomenon. Here it's classical. It's the frequency of classical oscillators. When we're discussing electronic states, it was the quantum mechanics of a coupled system of wave functions. So the physics is totally different. Quantum mechanics, classical mechanics. We give it the same name because the underlying mathematics is the same. So these are called phonon band structures, phonon bands or phonon band structures. Yes?
In our discussion, we assume that we are in one dimension.
Yes.
It means those atoms doesn't see the effect of the other one.
Yes, correct. So the question is, so far our discussion was limited to one dimension. So every atom doesn't see, well, a single atom doesn't see, well, our model, there's no other atoms, there's only one single chain. But your question is, what happens in 3 dimensions? What happens when you study a system in 3 dimensions? Well, the mathematics is not that different. The only thing you have to keep in mind is that these are not numbers, but they are vectors, 3-dimensional vectors. So when you start your, you remember the first equation we wrote at the blackboard was Newton's equations. M, acceleration of a given particle, and there you have the 3-dimensional vector. Okay, so you add m, and here we can write ui double dot as a vector in 3 dimensions, right? Then you simply have to write your springs in 3 dimensions. So you have to consider that if you're sitting here and the other particle is here and you have a spring, it's the force along this direction which will be affected by the spring. So you have to write it in vector form. So you have to add up vectors, not just numbers like we did here at the blackboard. It's a bit more complex, but the overall theory remains exactly the same. There's no major qualitative difference. It's just more mathematics because you have to do everything in 3 dimensions. But otherwise, it's just work with vectors instead of with numbers. Yes?
How much is the volume, the stiffness change?
Oh, how much in physical terms, the stiffness case is the stiffness of interaction between two atoms. So it's, you mean in which physical units? What would you like to know? I mean, in...
I think I thought it's like it's just like the energy per unit, something like the force per unit meter.
Not really, because it's the curvature, right? So the stiffness is not just the energy, it's the second derivative of the energy, or if you wish, the first derivative of the force. There is something, however, let me very quickly mention it because it's important. If you look at your universal curve of interaction, this one, right, between two particles, but more or less it's the same as for n particles, because even for n particles, it's the sum of interactions between pair particles to first approximation. So typically, when the binding energy is large, at the same time, the equilibrium distance is typically short, right? Strong bonds mean also that the bond is short. So a strong bond inevitably means that the curvature is very large. Weak bonds, on the contrary, are typically very shallow and the equilibrium length is very long. So the curvature is very small. So strong bonds, I mean, so you can correlate the binding energy with the stiffness. They go together. If the bond is stronger, the frequency will be, K will be larger, and therefore the frequency will be higher. Okay?
One thing, from the expression, I think omega is related to the mass. So I think
Yeah.
if the mass is to be, I don't know, I mean, in
Sure.
a sense, then we've lost some corrections, right?
We've lost some corrections.
We have some corrections.
Corrections. So the question is, if n is large, we will have some corrections. Which kind of corrections?
I don't know.
There was no point in our theory where we assumed that the mass was small, right?
Yeah, but yeah. Because we made some approximations.
Which approximations are you referring to among the ones that we've made? Now, there was no approximation among the ones we've made in which the size of m was relevant. There was probably only one, and this was when I'm writing Newton's equations. Newton's equations is something that holds for classical particles. So m must be large enough to be treated like a classical particle. That's probably the only approximation I can think of possibly affecting that statement. If the particle is too light, the question of whether Newton's equations are not applicable becomes an important one. Now, in practical terms, there are only a few, actually probably two systems for which classical Newton's dynamics is not so obvious that it works. And this is the lightest atoms, hydrogen and helium. Okay? Hydrogen, unfortunately or fortunately, forms diatomic molecules. Okay? So actually the object that you are dealing with is either a very stiff one or it's a heavier one because it's a combination of two molecules, two atoms. So the mass is twice the one that the nitrogen atom has. But anyway, for hydrogen and for helium, you might question the validity of the Newton, of classical mechanics. But these are really the only two systems in which you may consider questioning this approximation. Actually, the heavier, the better, because the more the particle behaves like a classical particle. That's the only place where mass entered in our discussion. Any other question? Yes.
In three dimension, we have different kinds of crystals with different number of Lewis tables. So how it can adapt for something like this?
We are going to discuss this next time, but essentially, well, okay, 2 minutes. Here we have now, if you wait, until next time, it becomes clearer. what happens in the case of more than one dimension. We're going to see the case of 2 atoms per unit cell, and then it becomes clear that if you have more than 1 degree of freedom per unit cell, whether it's because you have 2 atoms or because each atom has 3 degrees of freedom, the solutions will change. But allow me to wait until next time before I answer your question. It becomes much clearer. Yes, okay.
We say if the amplitude is 0 and is 0,
Yes?
then it means it stays there.
Yeah.
But I think it can also mean the whole thing is moving together. I don't know.
Right, okay. Yes, I mean, of course, we are not considering that kind of, this is not a vibration. The fact that the entire crystal is moving translationally, well, okay, it's a trivial kind of solution anyway, right? So it's, yeah, fine.
Like kind of diffusion, I don't know.
Yeah. I know what you're heading to, but I don't want to enter into the details because it otherwise would take me at least 10 minutes to explain. What you're saying actually is what we use to prove the sum rule that I mentioned before. Sum rule according to which the sum of all the elements in a row must sum up to 0 comes out precisely from your considerations that if you translate your system rigidly, there is no energy, there is no restoring force for that motion. If you actually do the calculation, find out that this implies that the sum rule must be satisfied. You may actually see it here. Yes, sorry, it's trivial. Because if U is, no, wait a second. Yes, if U is a constant, and the system moves rigidly, where was it? Ui bar is equal to U double bar e to the I qi. So suppose you move your system rigidly. All the atoms move at the same time. Then Q must be 0, right? Because all the atoms move with the same displacement. If Q is not 0, then the atoms will all move with a different displacement. So Q must be 0. So the kind of mode that you mentioned must be corresponding to Q equals to 0. And if Q equals to 0, Ui bar is equal to U double bar, period. So if Q is equal to 0, well, omega is equal to 0, and minus k plus 2k minus k must be 0. Okay? So it is 0, of course, because we built the model in such a way that it was self-consistent. But this is actually telling you that the sum of the 3 terms must be 0, whatever it is. It is, of course, 0 because we constructed the model correctly. But there is a sum rule on the sum of all these 3 terms, which comes from the fact that the solution with Q equals to 0. We'll come back to that next time. I think we'll spend 5 minutes on this next time. More questions? Yes. Sorry? Yes. With different what? What do you mean by different mode of oscillation? With same, sorry? Moving to the left. Okay. Well, we found some solutions of the problem. We will discuss them, tomorrow. Well, no, on next lecture. You're saying that if the starting point so you want to start with atom I moving to the right and atom I minus 1 moving to the opposite direction? And sure, okay. Go. Actually, if you wish, you can. Shall we just perhaps finish the lecture now? Then we take questions privately, so that we close the lecture now.